And next up, we have our very own organizer, Josh Michielsen, who is going to be talking about eBPF-ing what? An introduction to eBPF.
Now can everybody
Yep,
hear me?
we can hear
There
you.
we go. It helps when you turn the microphone on. Brilliant. So let's share my screen. Right. So the title of my talk today is eBPF-ing what? An introduction to eBPF. My name is Josh Michielsen. I am a senior software engineer at Sneak. We are a cloud native security company focusing on container security, open source dependency security, and the like. So I'm going to talk today about eBPF and effectively what it is. It's a bit of a complicated topic, and so hopefully we'll get most of the way through this talk and have a little bit of time at the end for a bit of a demo. But there's a lot to cover. So the first question is, what is eBPF? Well, eBPF is a revolutionary technology with origins in the Linux kernel, blah, 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 blah. So obviously a very self-explanatory piece of technology, but really sort of begs the question, seriously, what is eBPF? Well, eBPF stands for the Extended Berkeley Packet Filter. The Berkeley Packet Filter was created as part of the Linux kernel a long time ago. Was originally used for mostly around networking. So picking up networking packets, detecting and actioning on certain things within the kernel from a networking point of view. But that's not really what BPF is anymore, or eBPF for that matter. eBPF is a technology now. We refer to it as technology, and specifically it's a sandboxed bytecode and execution environment that lives within the Linux kernel. eBPF itself is a virtual machine that takes your bytecode, compiles it just in time to machine-specific machine code, and then executes it within the kernel. And we can use this to create software in the observability, networking, and security spaces. BPF programs, and I'm going to use BPF and eBPF kind of interchangeably throughout the talk. They both mean the same thing, really, when we talk about it these days. eBPF programs allow application developers to run custom code in the kernel to respond to events. And we can now do this without having to write things like kernel modules where you'd have to recompile your kernel and all this kind of stuff. We can load them in at runtime, and off we go. Programs for BPF are written in C, but it's a restricted version of C. They're compiled to bytecode in user space. The reason that we have to write them in a restricted version of C is because C itself, or at least within the context of the kernel, would lead to a potentially unsafe programming environment. So we're executing code in the kernel. We need to ensure some very strict safety of that code. And so things like loops, for example, are out. We can't have loops because we can't hold up the kernel anyway. We can't cause the machine to seize up, to stop working. And so we have to avoid writing our programs in a way that could lead to some sort of unsafe execution. Programs are loaded into the kernel via a system call, and that system call is the BPF system call, where they run through a verifier. The verifier does all those kinds of things. It's basically a static code analysis to ensure that the code that we're running isn't breaking any rules, basically. And then it's compiled into a machine-specific instruction set via the just-in-time compiler. eBPF maps are used to store and share data between the program in the kernel and the user space application. And we can also use maps to, share data even between different eBPF programs, of which we can run multiple. So this is a bit of a diagram to show you sort of how it works. So we have an application. We do a bytecode compilation in user space and then load that bytecode into the kernel via the BPF system call. The kernel will run it through the verifier and then through the just-in-time compiler, load it into the BPF virtual machine where it will execute based on the hooks that you set within your code. And then when those events occur, they will be injected into the BPF virtual machine. Your code will run, you store that in a map, and then your application can access that map. So what are some of the events that we can attach to? And I'll go into this in a little bit more detail down the road, but we can do K-probes, K-rep probes, U-probes, trace points, network events, and there's sort of a whole bunch more as well. There's trace events, perf events, stuff like that. The kernel provides us with helper functions that allow developers to call into the kernel itself to retrieve and store data, to do certain things that would be generally considered unsafe to do if you had direct access into the kernel. So we're going to take a moment to explore the eBPF ecosystem. I like this quote by Brendan Gregg. He's an engineer at Netflix. What is a quick and easy way to get a BPF performance win? And that is to think like a sysadmin and not like a programmer. The BPF ecosystem is huge and is growing rapidly at the moment. And there's a lot of amazing tools already out there that may already fill your needs without you having to go and write your own. So what are some basic tools? And basic in this particular case does not mean that they're simple or easy to make. What it means is that they're easy to use, really. You can, pull them from a repo or install them into your Linux machine through like apt-get or something like that, and then run them. So here is a nice, lovely diagram showing a whole bunch of different tools available to us. I didn't recreate this diagram myself, so you're going to have to put up with the sort of ugly image on an otherwise nice looking slide. That was just going to be too much work. So these are the BCC tools. BCC stands for the BPF compiler collection. And basically, these are just a whole bunch of Python tools that you can install into your environment, into your Linux environment, and just run them. And so an example of that is we have exec-snoop. And this allows us to basically capture and output processes that are run on the system by any user, and get things like return codes and things like that. So we have, in this particular case, this is just a really short example where I ran exec-snoop and threw out a couple of commands, ls, cat, etc. And here's what we get back. So we get the process ID, the parent process ID. We can get the args as well, the arguments sent to the process. And this is just running on a Linux machine with the BCC tools installed. You do have to run BPF programs as a privileged user, so you do have to sudo them for obvious reasons. I mean, they're code running in the kernel. So next up, we sort of have another program that's kind of similar called BPF trace. This is a collection, again, another collection of tools, but also a kind of custom programming environment at the same time that you can write some of your own functionality using a kind of custom language, basically. In this particular case, here's an example. So I run BPF trace, and I actually give it the command that I want. I want to get the raw syscall for sysenter, and then I want to count basically the commands that have been run. And so I ran this for 30 seconds to a minute on one of my machines, and we can see that it basically counts the number of times a certain command was run. In this particular case, apparently Node ran 38,500 times, which is both concerning but also not surprising with Node. So next up, we're going to move on to some projects, and these are open source tools and tools being used actively within the community. They're a little bit more difficult to get started with, but provide a ton of functionality out of the box. So the first one is Cilium. Cilium is an open source sort of networking, security, and observability tool. You can use Cilium for things like load balancing, network policy, flow and policy logging, and even get metrics. You can. It's often used as a CNI provider within Kubernetes, and I think Joseph yesterday actually did a talk talking about how RVU uses Cilium to do cross-cluster networking, which is pretty cool. The next up is Hubble, and Hubble is another Cilium-based project. It's built on top of Cilium and provides a sort of platform for networking and network security using eBPF. As you can see, I have a diagram down the bottom. It provides a sort of UI and CLI and all this sort of stuff that you can utilize to get a whole bunch of information out of your clusters in regards to the networking occurring. Next up is Falco. I don't think, from what I understand, Falco didn't originally utilize eBPF. It's what they call a cloud-native runtime security product by Sysdig. It's now a CNCF project. But in more recent times, they've started to utilize eBPF to implement a whole bunch of functionality. So you can do things like behavioral monitoring. They have a YAML-based sort of DSL that you can write rules and things like that for. You can run it on your systems as a container in a Kubernetes cluster and that kind of stuff. The next up is Tracy by Aquasec. This is a sort of newer project. Same sort of idea as Falco. The Tracy project has sort of two sub-projects. The Tracy eBPF, which utilizes the libbpfgo library that Aquasec themselves wrote, which is sort of a wrapper around libbpfgo, libbpf. And it attaches to eBPF events, and then you can use Open Policy Agent to detect behavioral patterns and then notify. You can print to standard out, post to webhooks, that kind of stuff. Catran. Bit of a different one, coming back to networking, but this utilizes XDP, which is I've got a slide later on explaining what XDP is a little bit, but it's basically a layer 4 load balancer created by Facebook. It claims to be blazing fast. Something that has recently come out. Again, a sort of newer project in the scene. And I think this is the final one, Inspector Gadget. Inspector Gadget is a project that is actually sort of wrapping a whole bunch of tools rather than being sort of one tool on its own. It takes some of the ideas from the sort of previous BCC tools and BPF trace that we saw before and creates a project that is able to be deployed into your cluster. You get a crew plugin, which is a kubectl plugin that you can run these tools on any one of your nodes within Kubernetes and get a bunch of information. Pretty cool project, in my opinion. So how do we actually develop BPF programs? So we'll go over some of the basics, and hopefully, if we have some time, we'll get into a demo. So as I mentioned before, eBPF programs attach to events within the kernel. You'll see these referred to as sort of hooks or events or things like that, but effectively, eBPF is an event-based system. So a kprobe is basically a kernel probe, and a krep probe is a return probe. So it allows you to create programs that will run before and after a kernel instruction is executed. And a good example of a bunch of different things that you can do with this are just capturing syscalls. So when a file is opened and when a file is closed, all this kind of stuff. When an executable is run on a system, a kprobe and krep probe are useful for capturing information about those executables. Trace points. Trace points are static access components in the kernel. And what static basically means is that they're codified by the kernel developers. They're made available as a stable form of an API, in terms of being able to inject your program and access those events. So, if you write a program for one kernel version, going forward, you can expect some sort of form backwards compatibility, which isn't always going to be the case with things like kprobes. uprobes and urep probes are very similar to the kernel probes that we've talked about before, but these hook into programs running in user space, and you can get additional information about those programs in user space. And then we have network events. So the express data path, which is XDP, traffic control, socket filtering. BPF was originally created as a networking, a kernel subsystem for networking. And so the networking aspect of BPF is huge. There's a host of different events that you can attach to. XDP, for example, provides early access to packets before the kernel stack actually processes them. So this is actually really useful for things like load balancers, where you can have an eBPF-based load balancer. And there's a fantastic talk by Liz Rice, who spoke at the eBPF Summit, who actually, she wrote an eBPF-based load balancer live in C as one of the keynotes. And I highly recommend you go watch that. It's actually really fascinating. Maps. So BPF maps are basically data storage. They're a generic data structure, and we kind of know what maps mean as programmers, but maps are actually a whole bunch of different data structures in terms of how BPF considers them. You can utilize maps to share data across different BPF programs, between BPF programs and the user space. When you create a map, you need to give it a few different bits of information. So the map type, and we'll see some examples of those in a moment. And then, the sort of key size, value size, max entries, that kind of stuff. So keeping in mind these things are written in C, so we need to provide, a memory footprint for these different aspects. And so some of the types that we have available to us are things like hash maps and arrays, obviously. But we have all sorts of different things as well. We have a perf event array. We have stack traces. We have LRU hashes, which are like least recently used sort of queues. So there's a whole bunch of things there. Arrays of maps, hashes of maps. Next up, we got helpers. Helper functions are it basically exists in eBPF in order to ensure that we have safe access into the kernel when our programs are executed. We can't interact directly with the kernel from within the BPF virtual machine, but the helper functions give us entry points into the kernel to do certain things. We use helper functions to do a variety of different things. We can interact with maps, we can manipulate network packets, we can get things like PIDs and the C group identifiers, network packets, that kind of stuff. A couple of examples of these helper functions. We have BPF get current com, which is the current process name. Pretty self-explanatory. And we have BPF get current PID and TGID. This provides you with a 64-bit data structure that in the first 32 bits, you get the process ID, and the last 32 bits, you get the thread group ID. Funnily enough, there's a bit of a gotcha with this particular helper function. The process ID is the process ID from the perspective of the kernel. So the process ID in this particular case is actually from user space is what you'd see as represented as the thread ID or thread group ID. And the thread group ID is in user space actually what you'd consider to be the PID or the process ID. So it's important to understand that sometimes there's a few gotchas with these helper functions, but there's tons of documentation available, man pages and all that kind of stuff. So how do we actually write BPF programs? So we have two sort of primary libraries for writing our C-based programs. The first is the BCC, or the BPF compiler collection. Basically a toolkit around that works around LLVM and things like Clang in order to provide us with a whole bunch of instrumentation and access to various bits and pieces in the C programming language, and then provides Python and Lua front ends. It's probably the most mature of the two. It's been around for quite a long time. The second one is libbpf, which is actually the official eBPF library maintained by the Linux kernel maintainers. So this is a more recent project. It's a little bit less mature, but provides some more low-level functionality. The interface is quite complex and can be confusing at times. But it also adds some functionality, some sort of interesting functionality, such as compile once, run everywhere, which has been a pretty significant challenge in the past with BPF programs, because they need to be compiled for the specific kernel headers for the machine they're running on. So having compile once, run everywhere is a huge step forward. As support for that continues to be rolled out into new kernel versions and things like that. And then we have libraries from the perspective of application development. So we have quite a few Go ones, Python, Rust, and a few others in various other languages. Sorry to the sort of Java and the Java fans out there and things like that, or PHP. You're a bit out of luck. You'll need to write your own, or just write code in a good language. I'm joking. Adrian's giving me a look. All right, so let's hop over to a quick demo. How am I going for time? We have 5 minutes. All right. So I have a Hello World program here. It is this is just a C file. I have a header file which just brings in some includes. Basically, we start off with this. I'll just create this, make this a little bit bigger. Hopefully, there we go. So in this particular case, we have this SEC function, which we pass in, the kprobe basically that we want to execute, or the attach to. In this case, we're attaching to a system call of exec_ve, and we are printing hello world to BPF print k, which is basically just a trace pipe that allows us to, we can then capture that later on, and I'll show you how to do that. And this is my Go code. The Go code for this particular example is actually quite a bit longer than the C code. I'm using the Cilium eBPF library to interface with this at the moment, but you can use any one of the ones that I mentioned or showed before on that slide. In this particular case, I have a Go generate declaration. If you're not familiar with Go, quite simple. When I run Go generate, it'll call out to this executable and basically run whatever the instruction is there. So in this case, I'm calling out to Clang, and it's creating, compiling or converting to Go code some information for me to be able to interface with my program. So we do a few things. I've just got like a signal notifier here for when I interrupt. We lock the memory for eBPF sources, and then we basically load our objects into the kernel, and we attach to the kprobe. And so what I can do is I've already compiled my program. So I can run my program, and then I can I'm going to forget the command for this. Give me a sec. I've forgotten the command in all my genius. Apparently it's not finding that in my reverse search. That's fine. Oops. And so if I create a new terminal real quick, I can run a few commands. If I hop back into here, it's now not working. Of course not. What we should be seeing there is a whole bunch of hello worlds popping out. It was working about 45 minutes ago. So, but I think you basically get the idea. I'm not sure why that's working now, and I don't have enough time to troubleshoot it. But I will have this code. I'll make sure it's working, and then I'll have this code up on GitHub, and I'll post it for everyone to have a look at. But that's a real simple example. I also have another example which I'll post as well, which is a little bit more complex. I know this one works for sure, which is actually using a trace point to capture our exec-v system calls and actually grab a whole bunch of new data, a whole bunch of data out of that, and then print it out. And so I'll upload both of those to GitHub and make them available for everybody. And on that note, I'm out of time, so I'll leave you with some pictures of my dogs, Sky and Maru, and I'll say thank you.
Okay, thank you very much, Josh. I think that was excellent. Demo gods aside, I think we all got where you're going with that demo. Yeah, so we've got a little bit of time. So as a quick question, one thing that always strikes me, I'm like eBPF really seems to be taking off, but it's quite a low level technology. So I'm always a little bit surprised by that. Yeah, and I'm kind of wondering, does the sort of average Kubernetes developer, would you expect them to benefit from learning eBPF, or should they expect to learn it? Or
honestly, I think for the average Kubernetes administrator, maintainer, or in terms of people maintaining clusters, for the most part, unless you have a real good reason to do so, unless you're working in the sort of runtime security space, or you're working in the networking, load balancing or security space there, or the observability space. There's a ton of work going on right now, especially in places like Datadog and like Elastic, where they're doing a ton of work with eBPF to get data out regarding application runtime observability and performance. So for the most part, I think the average person is going to be better off knowing about the existing tools that are out there that are taking advantage of eBPF and the sort of power that it brings. And it's a space that's growing really rapidly. And so I would expect to see a ton of innovation in that space for the next couple of years at the very least. But knowing what's out there and how to use those tools would be far more beneficial for the average person than being able to actually write your own.
yeah, so what you'd say is that it's basically enabling sort of the next generation of tooling on Kubernetes effectively and Linux in general.
Absolutely, yeah.
Cool. Okay, I don't think there was any other questions. Let me double check. I don't see anything. Let me check the YouTube actually. Okay. We do have a quick sponsor thing before I hand over to Danny. So yeah, we have several sponsors. We love you all. Control Plane, Storage OS, JetStack, Sneak, Tramshed, Sysdig, and our charity partners, Stimet and Protect Earth, but Storage OS. So Storage OS is a software-defined cloud-native storage platform delivering persistent storage for Kubernetes. Storage OS is built from the ground up with no legacy restrictions to give enterprises working with cloud-native workloads a scalable storage platform with no compromise in performance, availability, or security. For additional information, visit www.storageos.com. That was my best advertising voice. I like that. Okay, so no, but big thanks to Storage OS, and over to you, Danny.